form because I use that word for a different form. So I'm going to call that reduced echelon form. So a matrix or a linear system's in reduced echelon form if addition to being in echelon form. Not only do you have zeros below the diagonal, but you also have every entry on the diagonal is a 1 and every leading entry is a 1. And it's the only non-zero entry in its column. So you've pivoted on that entry and cleared completely out of that column. And again, the cost of Gauss-Jordan reduction is that it takes additional arithmetic. People have spent a lot of time what we're going to occupy ourselves with today is about the Gauss and with some. I have a method that's very neat. That not that be perfectly right. If I do Gauss's method on a matrix, any of the Gauss's method operations, if I do any of the Gauss's method operations, the elementary row operations on a matrix, then I can reverse them. Okay, I'm in fact, I as so that they are to each other. Phrase is to give of the first, so it will have other than. Fits for us also, but first, I do Gauss's method or Gauss-Jordan, which see final of that. If I do, then I can act made it myself not the case that the matrices do myself. I could go from that redo act from just operate, but I mean form to that's over to the up into commodities in one thing. So tricking is okay. So I'll put that slide up, and we'll see you then next time. Very good. Hi, hello. Okay, so last time we talked about Gauss-Jordan reduction, and we ended by talking about matrices being row equivalent. So today we're going to use the Gauss-Jordan reduction to make an observation about how to tell when matrices are row equivalent. I want to start by reviewing row equivalence. I want to, in the check-in, I want to give a quick sort of idea of what row equivalence is about. Okay, so the first question, really a couple of straightforward questions. Produce two matrices that are row equivalent, and then produce two matrices that are not row equivalent. It would be pretty silly if I had a relationship between matrices and all of them satisfy it. That'd be pretty silly. So let me do the first one. Produce two matrices that are row equivalent, and of course I can give all kinds of answers. I can give a matrix with itself, for example. That'd be silly but technically correct. But I want to get across something that makes the lesson for later on in the course. So so the idea here is I want to look at two matrices that are row equivalent to contain some concept. So the concept is that matrices are row equivalent when they contain somehow the same information. So my example of two matrices that are row equivalent is going to be this. How about 1, 1, 3, and 0, 1, 1 from my first matrix. And you know what? I'm going to make it an augmented matrix to make it look like a linear system, to make it look like I'm solving a linear system. And when I do, it would be natural to do the Gauss-Jordan step here of minus row 2 add to row 1 and end up with the matrix 1, 0, 2, 0, 1, 1. Those two matrices are row equivalent, and the row equivalence has a conceptual feeling here that the reason they're row equivalent, technically they're row equivalent, the reason they're row equivalent is that they contain somehow the same information. They, in this case, are supposed to represent linear systems with the same solution, namely x equals 2, y equals 1. So row equivalence has a meaning. It somehow contains, tries to capture that two linear systems are row equivalent when they say the same thing in some sense. In this case, they say that the linear system has that unique solution. Of course, I could have made up other row equivalences. I could have made up, say, a 3 by 3 matrix and done 3 or 4 Gauss method steps, and then I'd have two row equivalent matrices. That's all perfectly fine. I could have made up a matrix and then multiplied the first row by 5. That's all perfectly fine. But this one, I think, captures an idea. So let's see, what was the second question was to make up two that are not row equivalent. Okay, well, one cheap way, cheap answer, smart guy, wise Alec way to make up two matrices that are not row equivalent is to make up different sized matrices. 1, 2, 3, 4 is not row equivalent. I'll put a twiddle with a slash. Not row equivalent. That's just a symbol. 1, 2, 3, 4, 5, 6, 7, 8, 9. True, but not really showing any concepts. So maybe something that shows a little more in the way of concepts is, how about this one here? If I have 1, 0, 0, 0, 0, 0, and I contrast it with 0, 0, 0, 0, 1, 0. And now I can say, you can think of those as augmented matrices if you like. I won't bother to write in the vertical bar. Now, when I say they're not row equivalent, I'm making the observation that you cannot get from here to here by doing row operations. And the reason is simple. There's no ones in that column. There's no way you can manufacture a one. No combination of these two, of the 0 and the 0, will allow you to make a 1. Or going in reverse direction, no combination of these zeros will allow you to make that 1. So these two matrices are not row equivalent. So the relation row equivalent. Equivalence is not trivial. Some matrices are row equivalent. I know this is a silly way to be not row equivalent, but this is less silly. Some matrices are not row equivalent. And here I had in mind one more example. Suppose I look at 1, 0, 0, 0, 1, 1, and also I should have put a twiddle with a slash to it, and also 1, 3, 3, 0, 1, 1. Now these two matrices are row equivalent because I can get from the first to the second by some row operations. I can take 3 times row 2 and add to row 1. I take that linear combination 3 times row 2 and add to row 1, and that'll take me from here to here, or I can reverse it. I can do the Gauss-Jordan step of taking minus 3 row 2 adding to row 1 and get to here. They are interreducible. But if I contrast what's here with this one, 1, 3, 2, 0, 1, 1, there's no way to get from here to here. These are not row equivalent. There's no way to get from here to here, because if you're going to get a 3 there, you've got to get it by somehow using the 1. Using the 1. If you're using that 1, you've got to use this 1. So these two have to be the same number. So again, row equivalence has something to say about the linear content of this collection of rows. The linear content of this collection of rows. Somehow this collection of rows has a different linear content than this collection of rows, but this collection has the same as this. The question we want to address today is how can you tell when two matrices have the same sort of the same information in them. And I know, of course, that's all very vague, but we're going to make precise definitions today. We're working on it. We're working on it. Whoops, went to the wrong place. Sorry about that. There we go. Okay, so when I was first started teaching, I had a professor that I worked with. I was a teaching assistant for this professor who every day would say at least 15 times, this is very important. Well, when everything's important, then nothing's important. And Van Clausewitz made the same observation. He said a general that protects everything protects nothing. A general that defends everything defends nothing. And I hope that I've gotten pretty good about only saying this is important for those things that are really super important. This is super important. So the linear combination lemma is really at the heart of an awful lot of what we're going to be doing in the rest of the semester. So just to ask you to sort of pay sort of a special attention to what to what happens next. Okay, so the linear combination lemma. So I want to talk about how Gauss's method acts, and the way that it proceeds. Of course, we've seen it acting here. The way that it proceeds is illustrated by this simple Gauss-Jordan elimination here. Okay, so I eliminated below the diagonal. I changed the diagonal to ones, changed the leading entries to ones, and then I eliminated above. I'm going to call those matrices capital A, capital D, capital G, and capital B. I want to use delta and gamma for the letters for that matrix. Anyway, I'm going to call them by those letters. And then the point is that the steps that I go through, the minus 2 row 1 plus row 2, the minus 1/2 row 2, and the minus 3 row 2 plus row 1, the steps that I go through do something to the rows of the matrix. The rows of the second matrix, here first, second, the rows of the second matrix somehow reflect the rows of the first matrix, and it's just as straightforward. If you start off with alpha 1 and alpha 2 for the rows of A, then delta 1 and delta 2 it's just simply that delta 1 is alpha 1 and delta 2 is minus 2 alpha 1 plus alpha 2, because that's exactly what it says right here, is that you want to make the second row be minus 2 times the first row plus the second. So that might strike you as doesn't say anything you didn't know before. When I do the next operation, minus 1/2 row 2, of course, to get the matrix G, the rows now are that the first row of the matrix G, I call it gamma. First row of the matrix G is still alpha 1. The second row of the matrix G is half of the second row of the matrix D. So I halved everything. Minus 2 alpha 1 became alpha 1. Alpha 2 became minus 1/2 alpha 2. And last, I went from this matrix here to this matrix here with some kind of Gauss's method combination step. Minus 3 row 2 plus row 1, and now you see it happening. This is the matrix B. So row 1 of the matrix B and row 2 of the matrix B. Row 2 of the matrix B is the same as row 2 of the matrix G, because that's how we proceed. We leave the acting row unchanged, and the acted on row is the one that gets changed. So I took minus 3 row 2 plus row 1. Minus 3 times alpha 1 added to alpha 1 became minus 2 alpha 1. Minus 3 times minus 1/2 makes positive 3/2. Halves alpha 2 added to 0 alpha 2 became 3/2 alpha 2. So Gauss's method acts by taking linear combinations of the rows. The matrix at the end has linear combinations of the rows of the matrix at the beginning. We are studying linear combinations. Gauss's method proceeds by taking linear combinations. That's all this says. If you look in there, you're seeing linear combinations of the rows of the starting matrix. That's all it says. Small observation, but a lot of times big things are built on small observation. And the linear combination lemma is codifying that small observation. It says that a linear combination of linear combinations is a linear combination. What is that? What is that? What does that mean? So, for instance, if you take a linear combination like 4x1 plus 5x2, and another linear combination 7x1 plus 8x2, and you write them down, there's the 4 and the 5, there's the 7 and the 8, and you take a linear combination of those two, 3 times the first plus 6 times the second, what you end up with when all the smoke clears, 3 times 4, 6 times 7, that gives you 54. 3 times 5, 6 times 8, that gives you 63, if I did it right. If you take a linear combinations, two of them, and you find linear combinations of them, you end up with a linear combination. A linear combination of x1 and x2 combined with a linear combination of x1 and x2 gives you a linear combination of x1 and x2. A linear combination of linear combinations is a linear combination. It's a small observation, but an important one. Before we go on, I've got to give the argument, but before we go on, I'll just note that if you take quadratic combinations of quadratic combinations, just as an example, if you take quadratic combinations of quadratic combinations, what happens when you take quadratics of quadratics? Well, of course, you end up with all kinds of junk. You got third powers and fourth powers. So a quadratic combination of quadratic combinations is not a quadratic combination. There's something about linear. We're studying a property at least peculiar to linear. And the proof is taking this example and writing it down with A's and B's and C's sort of stuff. So I have a bunch of linear combinations of x1 through xn. There they are. And I take d1 times the first all the way down through dm times the last. And then just distribute d1s over the c's through dm over the c's, gather together all the x1s, gather together all the x1s and the xn's, and I end up with a linear combination of the x's. So this proof right here is simply putting into i's and j's what this example has in numbers. So the proof doesn't contain any content that the example doesn't contain, except that it shows how you do the proof. So it's a small observation. It's just a question of saying that's just a distributive law, but everything is easy once you know how. This one, it doesn't take you too long to know how. The statement, however, is the basis for what we will be doing for the rest of the course. A linear combination of linear combinations is a linear combination. You can take linear combinations and keep taking them and keep taking them and keep taking them. We saw that with Gauss's method, and you'll always have linear combinations. That is to say that we'll be working in systems that are closed under linear combinations. If you keep taking linear combinations, you'll never find yourself outside the system. And the corollary is just simply that when one matrix reduces to another, every row of the second is a linear combination of the rows of the first, and that's just the example that I started out by looking at with the matrices, A, D, G, and B. Okay, the proof is in the book, but the proof is just a question, as with the prior proof, of writing down what we already observed. Okay, so that leads me to another important observation that I need for today, and that is that there's something special about echelon form.
Hello.
There's something special about echelon form, and it is
Hello.
that if you have an echelon form matrix and you look at the non-zero rows, none of them is a linear combination.
बोला क्या तूने कुछ?
हाँ, कहाँ मरा हुआ है?
बोल रहा है क्या?
फोन तो क्या भाई, पिछले 5 मिनट से बोल रहा हूँ मैं।
चल फिर
बोल।
अभी आवाज आई है।
कहाँ हो? इतना उदास हो गए बैठे हुए दोनों।
पढ़ाई कर रहे हैं ना, पढ़ाई उदास करने की चीज।
क्या पढ़ रहा है?
मैथ्स।
और हिमांशु तू?
मैं फंक्शंस एंड पॉइंटर्स।
इतनी जल्दी पहुंच गया तू?
हाँ, सीख रहा हूँ लाइब्रेरी फंक्शंस क्या होते हैं, पढ़ रहा हूँ, बुक से पढ़ रहा हूँ।
बुक से कैसे कर लेता है तू?
हाँ यार, मैं भी यही सोच रहा
अबे
से
बुक से मुझे ज्यादा समझ में आता है, पता नहीं क्यों।
मैं नहीं कर पाता
भाई।
बुक से,
पता है,
मैंने रीड
पता है।
करके नहीं कर सकता, फिर उसको समझो, पहले रीड करो फिर प्रोसेस करो फिर समझो, इससे जब बंदा सामने कर रहा है वो सीधा समझ
हाँ,
लो।
वो ये भी मैं
नहीं,
सोचता हूँ
मुझे
मैंने।
वीडियो से पता नहीं क्यों ऐसा लगता है टाइम वेस्ट होता है।
उल्टा बुक
पता
से
है
टाइम
इस
वेस्ट होता है मुझे ऐसा लगता है, क्योंकि बार बार तुम्हें समझ इंग्लिश ही नहीं
हाँ,
समझ में आती आधा टाइम तो मुझे।
हाँ
ये
भाई,
क्या
सही
बोल
कह
रहा
रहा
है, बेटा अंकल ने देख लिया ना तो पीटेंगे भी।
तभी तो बुक से नहीं करता
यही
मैं।
इसीलिए पढ़ाया तुझे इंग्लिश मीडियम में।
है। अरे वो नहीं
वो
भाई, तू
बात
समझ
नहीं है।
नहीं रहा बात। अरे भाई,
हम्म।
बुक से पढ़ना ही मुश्किल है, क्योंकि उसमें कोई प्रैक्टिकल समझा नहीं रहा।
हाँ
हाँ
नहीं,
तो
है
भाई
यार इसमें,
पढ़ के,
है
भाई
इसमें
मतलब,
कोड्स।
वैसे वैसे
ये
बात
ब्लू में
सही
जो
कह
दे
रहा है
रखे हैं
भाई।
ना, कोड्स ही हैं।
तेरे भाई बात सही कह रहा है ये। बुक में ना
अच्छी
लोग
बात
लोग
है।
बुक से बहुत जल्दी सीखते हैं।
पढ़ो पढ़ो नहीं।
अरे मेन पता क्या होता है, मैं बताता हूँ। मुझे लगता है ना, कभी कोड विद हैरी में ना सारी इन्फॉर्मेशन नहीं दे रखी होती, जैसे वो 20 मिनट वाली वीडियो होती है। जैसे एरेस पे एक चीज बना दी तो मतलब पूरी इन्फॉर्मेशन नहीं होती, इसलिए मैं सोचता हूँ कि बुक से ना एक एक छोटी छोटी
तो
डिटेल्स दे
बिगनर
रखी
कोर्स
होती
है
है
ना,
कि ये करो।
बिगनर कोर्स करने के बाद तुम फिर हाई लेवल कोर्स पे जाओ।
अबे तो फिर वही है, हाई लेवल कोर्स कहाँ से ढूंढेगा फिर उसके बाद
अरे क्योंकि क्या होता है कि तुम जब बिगनर कर लो ना, तुम्हें उतना ही सफिशिएंट अमाउंट ऑफ नॉलेज चाहिए, फिर तुम्हें प्रोजेक्ट बिल्ड करने होते हैं, फिर तुम प्रोजेक्ट
अरे
बिल्ड
मतलब
करते हैं
पता
तो
है क्या होता है,
अपने
छोटी
आप
छोटी
सीखते
चीजें होती
रहते
है ना,
हो।
छोटी छोटी चीजें मैं ये बता रहा हूँ। जैसे
समझ गया
वो
समझ
जरूरी
गया
नहीं है छोटी।
समझ गया
वही,
समझ
अबे
गया।
मुझे ज्यादा समझ में आता है, बस यही
हाँ
मैं बता।
आता है ठीक है भाई बैच।
अरे अपने आप टाइम टू टाइम सब सीख लिया जाएगा भाई, चीजें कर करके ही सीखी जाएगी।
बंद कर दी क्या स्ट्रीम तूने?
नहीं चल रही
चल
है,
तो रही है।
चल रही है।
आवाज आ रही है यार?
हाँ
Combination of the others. If you have an echelon form matrix and you look at the non-zero rows, none of them is a linear combination of the others. And as with many of the things that we'll do in this class, the book contains the proof, and you should absolutely work through the proof. But in order to work through the proof, you need to have some understanding of what it's about. And so I'm doing an example here of what it's about, and I hope that a person can then go from that to seeing the same ideas in I's and J's.
क्या बकचोद की करा
All
है।
right, so I wrote down a matrix that is in echelon form. I want to show that no row is a linear combination of the others. It so happens that in order to best illustrate the proof, the thing I should do is to show that the middle row, 0567, 0567, is not a linear combination of 1, 2, 3, 4, and 0008. Okay, so I want to show that there's no linear combination that gives you this. And it's just a question of proceeding in two steps. The first step is to look at the first column. That is to say, look at columns to the left of the 5. To look at the first column. If you look at the entries in the first column, you have a 0, a C1 times 1, and a C3 times 0. A 0, a C1 times 1, and a C3 times 0. Well, when you look at that relationship, it's obvious that C1 has to be 0. So again, I'm looking only at the first column, the 0, the C1 times 1, and the C3 times 0. When you think about that relationship, of course, it's clear from that the C1 has to equal 0. So the C1 equals 0, so you can sort of take your finger and cover that part up. That part's gone now. We've concluded that if this relationship is going to hold, then C1 has to be 0. So we're now down to 0567 equals C3 times 0008. Okay, and now isn't it clear what to do next? Whoops, I hit the wrong button. And now isn't it? Okay, and now isn't it? they simply don't contain the same linear information. It might seem like a small difference, but that's all it takes, just that one, to make that difference. Okay, a comment about the proof here. So the proof is a lot of i's and j's, a lot of subscript i's and j's. Basically, you do what's called mathematical induction, and again, some folks will have seen mathematical induction, and some folks will have not. So I'm tending to there's a description in the back of the book in the appendix. I'm not embarrassed about it, but I'm tending to downplay the mathematical induction part in favor of the linear algebra part. So that's why. So remember to see both interread parts it in something to say that to see after so row and check saw not and augment. There we go. Yay! So next time we're going to talk about a new chapter, vectors, and so we'll start in with something brand new. Okay, very good. Bye bye. Hi, hello, hi. So last time we. Hi, hello, hi. So last time we finished the first chapter, and one of the lessons of the first chapter was that we are studying linear combinations. When we're talking about solving linear systems, we're really talking about taking linear combinations of the rows. We're studying linear combinations. So in this chapter, we want to expand what linear combinations are about, so that today's check-in is that first step in that direction. Here I have a linear combination of three vectors, not a linear combination of numbers like we saw in a lot of the previous chapter, but a linear combination of three vectors. We've already seen some of this when we wrote the solution sets of linear systems and when we wrote the equations of planes, but nonetheless I'm making it explicit here. This is a linear combination of three vectors and we're asked to solve it. So we're thinking about what can happen when you try to do equations involving these objects. Okay, so let's write it down. So I want to take the linear combination of those three vectors, and so write it down. We're asked to solve it.
मेरे तो ऊपर से जा रहा है यार ये कॉन्सेप्ट ही.
क्या बोला?
जन चला गया क्या?
नहीं
भाई ऊपर से जा रहा है यार.
क्या एक सेकंड रुकना, तू पढ़ क्या रहा है मैथ्स में?
लीनियर
मैट्रिसेस कर रहा है
अलजेब्रा.
क्या? मुश्किल है क्या इतना?
अरे यार ये वेक्टर से लिंक कर रहा है, सोच समझ नहीं आ रहा वेक्टर से क्या लिंक करी जा रहा है इसको.
तू अपना पहले कॉलेज में भी तेरे
वेक्टर से लिंक क्यों नहीं होगा भाई? मैट्रिसेस
होगा. छोड़ो तुम करो अपना.
अब 3D स्पेस में भाई मैट्रिसेस इज ऑल अबाउट 3D स्पेस.
अबे ये
अब 3D स्पेस में वेक्टर्स नहीं होगा तो कैसे होगा? काश अंकल देख लेंगे.
अरे क्या बोलूं, मैं समझ नहीं आया, ये टॉपिक ही समझ नहीं आया. मैं दूसरी वीडियो से देखता हूँ किसी थोड़ा सा ये वाला टॉपिक.
मैं तुझे जब बता रहा हूँ वो देखो MIT ओपन कोर्सवेयर, तो बंदा बांध नहीं मार रहा है. मैं तेरे लिए सच बता रहा हूँ भाई. एकदम ऐसे समझा देंगे ना, कोई तुझे समझा नहीं पाएगा वैसे. या तो ज्ञानेंद्र एक है हिंदी में पढ़ाते हैं, ज्ञानेंद्र पुरोहित.
वो
बेटा
तो
वो
मैंने
सर भी
भी
अच्छा
देखा
पढ़ाते हैं.
है. MIT ओपन कोर्स से भी देख लेता हूँ यार. MIT ओपन कोर्स मैं सारे कोर्स देख लूंगा, सब खत्म कर दूंगा, टॉपर बन जाऊंगा लीनियर अलजेब्रा का. अपना कोर्स बना
फाड़
के
दूंगा
बेचूंगा, सब फाड़ दूंगा.
कब है पेपर? कब है पेपर?
3 दिन में, 2 दिन में, 1 दिन में.
कब है?
1 दिन में कल.
अब कर लेना.
अरे एक पेपर का मुझे फ़र्क नहीं पड़ता, मुझे कॉन्सेप्ट समझ आना चाहिए, जब तक मज़ा नहीं आता तब तक मैं पढ़ता नहीं। नहीं सच्ची में, कहाँ देखिए देखिए, स्क्रीन शेयर कर ही रहा हूँ, बताइए वो कहाँ पर है एमआईटी का।
हाँ स्क्रीन शेयर कर।
हो ही नहीं रही, क्या बेवकूफ़ सॉफ्टवेयर है ये।
इतनी स्ट्रीम में कर देंगे ना हम, इतनी स्ट्रीम में कर देंगे किसी ने सोची ना होगी।
यूट्यूब भी बोलेगा इन्हें, तो मैं वायरल करके रहूँगा।
क्लाउड सर्विस इनके लिए थोड़ी था। जा फाइंड कोर्सेज।
जा रहा हूँ।
सबसे में ये जा टॉपिक वाइज।
कहाँ पे?
टॉपिक वाइज वैसे मोस्ट फेमस कोर्सेज में भी आ जाएगा टॉपिक। चल टॉपिक कर टॉपिक। हाँ अब उससे सिलेक्ट करो इंजीनियरिंग।
इंजीनियरिंग,
कंप्यूटर साइंस इंजीनियरिंग।
आर्टिफिशियल इंटेलिजेंस।
हाँ शायद उसमें आ जाए, पहले इसमें सर्च करके देख एक बार।
मैं तो है ही
आर्टिफिशियल,
नहीं।
शायद इसमें वैसे ही आ जाए, नीचे लिखा हुआ। एक बार देख लीनियर अलजेब्रा।
आर्टिफिशियल इंटेलिजेंस।
ये इसमें कंप्यूटर ओरिएंटेड अगर कोर्सेज आ रहे हैं ना, तो फिर
हाँ,
तू पता है क्या कर, डिपार्टमेंट मैथमेटिक्स कर, वो सॉरी टॉपिक मैथमेटिक्स कर। अगर इसमें वो सिर्फ इंजीनियरिंग के आ रहे हैं तो मैथमेटिक्स कर उसमें। इसमें इसमें इंजीनियरिंग है ना, मैथमेटिक्स का ही टॉपिक होगा देखियो, है ना। हाँ अब उसमें कर।
अलजेब्रा एंड नंबर थ्योरी।
हाँ उसमें होगा इंट्रोडक्शन टू लीनियर अलजेब्रा ऐसे कुछ होगा।
अलजेब्रा 1, अलजेब्रा 2।
लीनियर अलजेब्रा लिखा होगा उसमें, लीनियर अलजेब्रा लिखा होगा।
इंट्रोडक्शन टू।
मुझे मैं भेजता हूँ, मेरे पास है शायद, मैंने
पहले
शॉर्टकट कर रखा है
पहले नहीं बेच
शायद।
सकता था।
गालियाँ भी
इंट्रोडक्शन टू
पढ़-
लाई ग्रुप्स, अलजेब्रिक ज्योमेट्री। मुझे ये लग रहा है अलजेब्रा 1, अलजेब्रा 2। नहीं, अंडर ग्रेजुएट का है तो।
रुक जाना।
नहीं, हम अंडर ग्रेजुएट ही तो है हम।
हाँ तो तुझे क्या लगा अभी तक।
हाँ, हम तो अंडर ग्रेजुएट ही है।
फ्लाइट मेथड, ये रहा ना लीनियर अलजेब्रा पागल, दिख ही नहीं रहा है बंदे को।
कहाँ है
क्या यार कैसे जाएगा रे कैसे।
भाई? जब मिल जाए तो बता
उसमें कर, अलजेब्रा एंड नंबर थ्योरी से नीचे कर।
दे। कहाँ है
अबे
अलजेब्रा?
ऊपर 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 जहाँ वो सिलेक्ट किया, हाँ इस पे नीचे कर, नीचे सब टॉपिक में।
अच्छा, सब टॉपिक में बोलना, फिर मैं इधर देख रहा था।
सब मैं बता दूंगा, तू क्या करेगा भाई।
कहाँ है इंट्रोडक्शन टू लीनियर अलजेब्रा? अभी भी नहीं है।
हो ही नहीं सकता ऐसे, हो ही नहीं सकता मेरे भाई।
देख ले भाई, नहीं है।
इंट्रोडक्शन टू, रुक जा, लीनियर अलजेब्रा लिखा नहीं है।
नहीं है
फॉल 2013,
लीनियर अलजेब्रा
अंडर
तो लिखा
ग्रेजुएट।
हुआ है।
हाँ तो वही है।
2011 फॉल। ऐसे लीनियर अलजेब्रा 1 2 लिखा आ रहा था, अलजेब्रा 1 2 लिखा आ रहा है, देख।
रुक जा मैं बताता हूँ।
हम ये रहा लीनियर अलजेब्रा फॉल 2013 अंडर ग्रेजुएट।
हम्म।
ये है तेरा?
हाँ
पक्का?
वीडियो लेक्चर्स वाला देख, एक है वीडियो लेक्चर्स वाला भी है।
ये वीडियो
इसी में
लेक्चर्स
कर
वाला नहीं है ये?
है भाई है।
अरे ये वीडियो लेक्चर्स वाला नहीं है क्या? व्यू कोर्स।
2011 के फॉल वाला देख, उसमें है सारी वीडियो लेक्चर्स।
ये वाला फेल लिखा हुआ है, फॉल लिखा है, फेल लिखा है।
फॉल होता है भाई, वही है थोड़ा सा, मतलब पता क्या होता है। हाँ ये वाला ये रहा।
वीडियो लेक्चर्स।
हाँ उसमें जो तुझे टॉपिक देखना है देख ले।
ओए ये क्या है? इससे अच्छा मैं यूट्यूब पे ना सर्च कर लीनियर जब एमआईटी कोर्स पूरा ही आ जाए।
हाँ वाह यार तेजस, यू हैव बिकम इंटेलिजेंट पर्सन।
एमआईटी कोर्स
ये क्या देखते हो, कैजुअल रिलेशनशिप्स।
पे है।
अच्छी चीज है ये सब, देख
लीनियर
यही
अलजेब्रा
वाला
फॉर
ऊपर वाला
2000।
ऊपर वाला ऊपर वाला गिलबर्ट ये अच्छी है यार।
गिलबर्ट स्ट्रंग।
हाँ हाँ, है तो वही चीज, वहीं से स्टार्ट होगा मतलब।
10 लेक्चर 1। एक
हाँ
एक घंटे के कितने? 35 लेक्चर हैं। इन्हें देखना है मुझे।
हाँ
पूरी लीनियर अलजेब्रा करा
भाई,
दूं?
अच्छे से समझ में आएगा फिर।
पूरी
हाँ
पूरी करा देगा, सच बोल।
हाँ, दोनों देखें।
दोनों तूने भी देखनी है क्या स्टार्टिंग से?
अबे मैं तो यार तुझे क्या बताऊं, मैं तो एकदम मेरे को तो समझ ले कि मेरे को डायलेमा हो गया है।
डायलेमा? डिलेमा?
डिलेमा डायलेमा जो भी बोल दे भाई। पता है किस चीज में? या तो मैं एनडीए कर लूं, तो एनडीए के लिए 11 12 का पढ़ लूं अप्रैल तक। या तो
तूने
मैं
ये कर रखा है?
हैं?
ये लीनियर अलजेब्रा कर रखा है तूने?
अबे मतलब नहीं कर रखा ना, तभी तो बोल रहा हूँ। तो मैं यही सोच रहा था कि क्या, या तो मैं ये कर लूं। मैंने इसके 2 3 लेक्चर देख लिए। उसके बाद मुझे लगा यार इसमें टाइम लग रहा है, 2 2 घंटे, 2 2 घंटे मुझे एनडीए के मैथ्स में देना चाहिए, क्योंकि मेरे 2 महीने बाद पेपर है। यही है, मैं
अब
सोच
लेकिन
नहीं पा रहा
मैंने
हूँ।
तो
बता यार,
बेसिक
तू
पढ़
दोस्त
रखा
है, तू
है,
बता
मैंने तो
क्या करूँ।
पहले, अब ये हम इसका कोर्स अगर हम जीरो से स्टार्ट कर रहे हैं तो मैं तो पहले भी कर रखे हैं, अब ये हो जाना चाहिए।
हम्म।
अरे अब पापा देखेंगे, अब पापा को लगेगा कि मैंने कुछ भी नहीं पढ़ा, मैं जीरो से स्टार्ट कर रहा हूँ।
फोन कर रहे हैं क्या?
नहीं, मैं सोच रहा हूँ अगर देखेंगे तो बोलेंगे।
आप सुन लेंगे, टेंशन मत ले।
देख ही
मैं
लेंगे।
क्या बता रहा हूँ, तू यार बता यार मुझे क्या करूँ।
देख ले यार, कुछ भी करना है।
अबे तो कुछ तो तू तो बता, तेरे से मदद लेने आया हूँ, तू बता नहीं रहा।
अब तेरा गोल पे डिपेंड करता है, तुझे एनडीए करना है कि तुझे इंजीनियरिंग करनी है।
एनडीए करना है, सही बोला। अब तूने सही बोल दिया। मुझे वही करना है।
गोल पे डिपेंड।
चल तू फिर ये कोर्स कर, ठीक है।
35 वीडियोस का, अगर मैं इसको
शुरू कर, शुरू कर, मेरे सामने ही है, टाइम मत वेस्ट कर।
एक दिन में 24 घंटे होगा, अगर मैं 24 घंटे भी करूँ तो भी मुझे 2 दिन लग जाएंगे।
10 दिन का, 10 तारीख का हमने वो रखा था।
कर दूंगा
कितने
खत्म।
नादान थे अब।
कर दूंगा खत्म, बोल।
चल ठीक है, देखता हूँ। 3 घंटे देखेगा, 3 घंटे प्रैक्टिस करेगा, 6 घंटे, 6 घंटे से
तो
मैथ्स को देगा।
प्रैक्टिस नहीं कराएगा ये मुझे बीच में 1 घंटे के?
हैं?
1 घंटे में प्रैक्टिस नहीं कराएगा मुझे बुढ़ा?
अबे नहीं, ये सब लेक्चर्स होंगे। अच्छे से कॉन्सेप्ट की क्लैरिटी होगी, क्वेश्चंस होंगे। पर भी असाइनमेंट्स करेगा तभी तो अच्छे से क्वेश्चंस बनेंगे भाई।
वाहिगुरु।
असाइनमेंट्स करियो भाई इसके। असाइनमेंट्स देखा नहीं है? हर लेक्चर के बाद एक असाइनमेंट का वो होगा। वो असाइनमेंट्स करियो भाई, तभी तो बन पाएगा बढ़िया लीडर।
लीडर ने महंगे ने पाउंदे ने जट ते नारा ते फ्लैक्स, ना शौक मिटाइए कम ते चाहिए, कर दी ने अपने चाहे। गड्डी तू वेख मिली है फिफ्ट, पोर्शे
शुरू कर,
काली,
टाइम मत वेस्ट
शिफ्ट
कर।
या शिफ्ट, गैस से तू आ।
शुरू
साक्स।
कर, शुरू कर।
This is the first lecture in MIT's course 1806, linear algebra.
क्या हुआ?
टीम क्यों बंद कर दी?
तू भी देख रहा है?
मैं देखता ना तू कितना पढ़ रहा है। तेरे से क्वेश्चन पूछूंगा, तू दिखा।
भाई वो तो स्ट्रीम पे चल ही रहा है, देख ले जाके, ऐसे क्यों बन रहा है भाई अपने आप को?
सही कहा मेरे भाई तूने, सही कहा। पढ़ ले, वरना अंकल देखेंगे,
Algebra,
बोलेंगे डिस्टर्ब करता रहा।
and I'm Gilbert Strang. The text for the course is this book,
कितने घंटे चलाएगा
Introduction
भाई
to
स्ट्रीम?
Linear Algebra.
आज तो
And,
12 घंटे की चलेगी, सुबह 12 बजे तक। देख तू, जब दिमाग खराब होता है ना सरदार का, कुछ भी कर देता है। बस आधे
एक भी लाइक नहीं है। अंकल को बोल दे लाइक कर दो अंकल प्लीज।
बस आधे घंटे में मुझे नींद आ जाए।
लाइव स्ट्रीम पे सो जा।
the course webpage
लाइव
has got
स्ट्रीम,
a lot of
लाइव स्ट्रीम चालू है, न्यूज़ हो।
exercises from the past, MATLAB codes. The syllabus for the course is web.
12 घंटे एक स्ट्रीम करते हैं। 12 hours ऑफ स्लीपिंग नॉन स्टॉप।
ट्विच पे होती
हाउ
है,
कैन?
ट्विच पे होती है, पता है? ट्विच पे होती है, ट्विच पे लोग पैसे भी कमाते हैं ऐसे सो के।
हैं?
लोग उन्हें देखते हैं और लोग सुपर चैट करते हैं।
अच्छा, तो हम भी करते हैं। 12 hours ऑफ नॉन स्टॉप स्लीपिंग, हाउ कैन आई स्लीप फॉर 24 hours
And this is the first lecture, lecture 1.
विदाउट
So,
ओपनिंग माई आईज।
and later we'll say which we're giving
सारे
web
पैसे
address
कमा लूंगा
for viewing
एक ही
these
दिन में।
videotapes. Okay, so what's in the first lecture?
चल भाई, बुड्ढा पढ़ाना शुरू हो गया। ओए ये कैसा ब्लैक बोर्ड है?
हैं? तू तो उसमें कोचिंग में गया था, तूने नहीं देखा ऐसा ब्लैक बोर्ड
ये
कभी?
ऊपर हो गया।
तूने देखा कभी ब्लैक
नहीं।
बोर्ड ऐसा? कोचिंग में जाता था कि नहीं जाता था
वहां
तू
तो
विद्या
व्हाइट बोर्ड
मंदिर?
होता था सिंपल, एज जैसे स्कूलों में होता है।
नहीं पता क्या होता है, रोलर होता है, ऐसे कर देते हैं, ऐसे कर देते हैं, अभी नीचे खींच लेगा
हैं?
ऐसे। हाँ,
ओ भाई साहब,
तभी मैं कहता हूँ एमआईटी में हमारा जाने का फायदा था, हमने खाम
This
का ही
is
ले
my
लिया यहाँ
plan.
एडमिशन। मुझे तो बुला रहे थे एमआईटी
The
वाले,
ऊपर कर दिया साले ने।
fundamental
मुझे बुला रहे थे,
problem
मैंने
of
कहा नहीं
linear
मैं नहीं आ
algebra,
रहा।
which is to solve a system of linear equations. So let's start with the case when we have some number of equations, say n equations,
गाना भी गा
and
रहे थे मेरे लिए कि मेरे घर आ जाना।
भाई तेरा भाई नया रजिस्टर निकालेगा आज।
तू यार, तो पढ़ने का मन नहीं है तेरा, मैं समझ गया।
मैंने कब का पढ़ने का मन नहीं है, 3-4 घंटे, 2 2 ढाई घंटे होने वाले मुझे पढ़ते हुए। 12 बजे पूरे शुरू कर दिया था। अब मेरी ज़िंदगी का यही गोल है, लीनियर अलजेब्रा। जब तक मैं लीनियर अलजेब्रा नहीं कर लेता तब तो मैं इस चेयर से उठूंगा नहीं। इसी चेयर पे सोऊंगा, इसी चेयर पे खाऊंगा, इसी चेयर पे पोटी से शुरू करूँगा। नहीं, वो ज़्यादा हो जाएगा पोटी से करने
चल
का।
एक काम करते हैं, एक काम करेगा, कंपटीशन लगाएगा,
चल।
कंपटीशन से मजा आएगा। ठीक
हाँ
है,
हाँ।
मैं भी जा रहा हूँ, देखूंगा, तू भी देख।
चल
2 लेक्चर देख के क्वेश्चंस पूछेंगे एक दूसरे से,
चल ठीक
आज ही
है।
आज ही आज
आज ही
सोने
आज,
से पहले।
चल ठीक है, चल ठीक है,
2 लेक्चर्स का,
हाँ
ठीक है।
ठीक है, डन।
जीत के दिखाइयो मेरे से।
चल ठीक है, डन।
ठीक है, और अंकल आप देखते रहना, अगर हरा दिया ना तो मुझे इनाम देना। अब तू देख बेटा, तुझे हरा के दिखाता हूँ।
चल ठीक है, आजा बेटे, आजा।
ठीक,
आजा,
जा
तेरी
रहा हूँ मैं म्यूट,
तेरी फाड़
म्यूट जा
दूंगा
रहा हूँ।
देख तू आज।
ठीक, 2 घंटे बाद मिलते हैं, ठीक है।
2 घंटे बाद मिलते हैं, 2 से 4।
नहीं, मैं जब हाई करूंगा, उससे जिसने पहले कंप्लीट कर लिया वो भी जीतेगा।
ओह अच्छा, सी यू सून। यू आर
See you
हियर
soon.
ना, यू आर हियर ना, योर कैमरा इज ऑन ना।
हाँ,
ठीक है, सी यू सून।
n unknowns. So an equal number of equations and unknowns. That's the normal nice case. And what I want to do is, with examples of course, to describe first what I call the row picture. That's the picture of one equation at a time. It's the picture you've seen before in 2x2 equations where lines meet. So in a minute you'll see lines meeting. The second picture, I put a star beside that because that's such an important one. And maybe new to you is the picture a column at a time. And those are the rows and columns of a matrix. So the algebra way to look at the problem is the matrix form in using a matrix that I'll call A. Okay, so can I do an example? The whole semester will be examples and then see what's going on with the example. So, take an example. 2 equations, 2 unknowns. So let me take 2x minus y equals 0, let's say, and minus x plus, say, 2y equals 3. Okay. I can even say right away, what's the matrix that is, what's the coefficient matrix? The matrix that involves these numbers. A matrix is just a rectangular array of numbers. Here it's 2 rows and 2 columns. So 2 and minus 1 in the first row, minus 1 and 2 in the second row. That's the matrix. And the unknown, well, we've got 2 unknowns. So we've got a vector, x with 2 components, x and y, and we've got 2 right-hand sides that go into a vector 0, 3. I couldn't resist writing the matrix form even before the pictures. So I always will think of this as the matrix A, the matrix of coefficients. Then there's a vector of unknowns. Here we've only got 2 unknowns. Later we'll have any number of unknowns. And that vector of unknowns, well, I'll make that x extra bold. And the right-hand side is also a vector that I'll always call b. So linear equations are ax equal b, and the idea now is to solve this particular example and then step back to see the bigger picture. Okay, what's the picture for this example? The row picture. Okay, so here comes the row picture. So that means I take one row at a time, and I'm drawing here the xy plane, and I'm going to plot all the points that satisfy that first equation. So I'm looking at all the points that satisfy 2x minus y equals 0. It's often good to start with which point on the horizontal line. On this horizontal line, y is 0. The x-axis has y is 0, and that, in this case, actually, then x is 0. So the point, the origin, the point with coordinates 0, 0, is on the line. It solves that equation. Okay, tell me, well, I guess I have to tell you, another point that solves this same equation. Let me suppose x is 1. So
y
I'll
2
take x to
or
be 1.
x1.
Then y should be 2, right? So there's the point 1, 2 that also solves this equation. And I could put in more points. But let me put in all the points at once, because they all lie on a straight line. This is a linear equation, and that word linear has got the letters for line in it. That's the equation. This is the line of solutions to 2x minus y equals 0, my first row, first equation. So typically maybe x equal a half, y equal 1 will work. And sure enough, it does. Okay, that's the first one. Now the second one is not going to go through the origin. It's always important. Do we go through the origin or not? In this case, yes, because there's a 0 over there. In this case, we don't go through the origin because if x and y are 0, we don't get 3. So let me again say, suppose y is 0. What x do we actually get? If y is 0, then I get x is minus 3. So if y is 0, I go along minus 3. So there's one point on this second line. Now let me say, well, suppose x is minus 1. Just to take another x. If x is minus 1, then this is a 1.
1
And
फिर होते
I
जा
think
2
y should be a
1
1.
y is equal to 1.
Because if x is minus 1, then I think y should be a 1, and we'll get that point. Is that right? If x is minus 1, that's a 1. If y is a 1, that's a 2, and the 1 and the 2 make 3, and that point's on the equation. Okay, now I should just draw the line, right? Connecting those 2 points, that will give me the whole line. And if I've done this reasonably well, I think it's going to happen to go through, well, not happen, it was arranged to go through that point. So I think that the second line is this one, and this is the all-important point that lies on both lines. Shall we just check that point, which is the point x equal 1 and y was 2, right? That's the point there, and that, I believe, solves both equations. Let's just check this. If x is 1, I have a minus 1 plus 4 equals 3. Okay. Apologies for drawing this picture that you've seen before. But seeing the row picture, first of all, for n equal 2 equations and 2 unknowns, it's the right place to start. Okay, so we've got the solution, the point that lies on both lines. Now can I come to the column picture? Pay attention. This is the key point. So the column picture. I'm now going to look at the columns of the matrix. I'm going to look at this part and this part. I'm going to say that the x part is really, is really x times, you see I'm putting the two, I'm kind of getting the two equations at once. That part, and then I have a y, and in the first equation it's multiplying a minus 1, and in the second equation a 2, and on the right-hand side, 0 and 3. You see the columns of the matrix? The columns of A are here, and the right-hand side B is there. And now what is the equation asking for? It's asking us to find, somehow to combine that vector and this one in the right amounts to get that one. It's asking us to find the right linear combination. This is called a linear combination. And it's the most fundamental operation in the whole course. It's a linear combination of the columns. That's what we're seeing on the left side. Again, I don't want to write down a big definition. You can see what it is. There's column 1, there's column 2. I multiply by some numbers, and I add. That's a combination, a linear combination, and I want to make those numbers the right numbers to produce 0, 3. Okay. Now I want to draw a picture that represents what this is algebra. What's the geometry? What's the picture that goes with it? Okay. So again, these vectors have 2 components, so I better draw a picture like that. So can I put down these columns? I'll draw these columns as they are, and then I'll do a combination of them. So the first column is over 2 and down 1, right? So there's the first column. The first column, column 1. It's the vector 2 minus 1. The second column is, let's see, I go over minus 1 is the first component and up 2. It's here. There's column 2. So this, again, you see what its components are. Its components are minus 1, 2. Good. That's this guy. Now, now I have to take a combination. What combination shall I take? Why not the right combination? What the hell? Okay. So the combination I'm going to take is the right one to produce 0, 3, and then we'll see it happen in the picture. So the right combination is to take x as one of those and 2 of these. It's because we already know that that's the right x and y, so why not take the correct combination here and see it happen? Okay, so how do I picture this linear combination? So I start with this vector. That's already here. So that's 1 of column 1. That's 1 times column 1, right there. And now I want to add on. So I'm going to hook the next vector on to the front of the arrow. We'll start the next vector, and it'll go this way. So let's see. Can I do it right? If I added on one of these vectors, it would go left 1 and up 2. So it would go left 1 and up 2. So it would probably get us to there. Maybe I'll do dotted line for that. Okay? That's 1 of column 2 tucked on to the end. But I wanted to tuck on 2 of column 2. So that the second one will go up left 1 and up 2 also. It'll probably end there. And there's another one. So what I've put in here is 2 of column 2 added on. And where did I end up?
0,
What
3.
are the coordinates of this result? What do I get when I take 1 of this plus 2 of that? I do get that, of course. There it is. There it is. X is 0. Y is 3. That's B. That's the answer we wanted. And how do I do it? You see, I do it just like the first component. I have a 2 and a minus 2. That produces a 0. And in the second component, I have a -1 and a 4. They combine to give the 3. But look at this picture. So here's our key picture. I combine this column and this column to get, maybe I better, to get this guy. That was the B. That's the 0, 3. Okay. So that idea of linear combinations is crucial. And also, do we want to think about this question? Sure, why not? What are all the combinations? If I took, can I go back to x's and y's? This is a question for really, it's going to come up over and over, but why don't we see it once now? If I took all the x's and all the y's, all the combinations, what would be all the results? And actually, the result would be that I could get any right-hand side at all. The combinations of this and this would fill the whole plane. You can tuck that away. We'll explore it further. But this idea of what linear combination gives B and what do all the linear combinations give, what are all the possible achievable right-hand sides be, that's going to be basic. Okay, can I move to 3 equations and 3 unknowns? Because it's easy to picture the 2x2 case. Let me do a 3x3 example. Okay, I'll sort of start it the same way, say maybe 2x minus y, and maybe I'll start 2 because it's easy to decide.
समझ में आ रहा है?
ओ भाई डरा दिया
बोलना,
डरा दिया तूने, पता है मैं तो
समझ में आ रहा है?
घुसा हुआ था उसके अंदर। हाँ हाँ, क्यों नहीं आ रहा?
अबे यार, कहाँ पहुंचा है अभी तक तू? अभी 20 मिनट पे ही है क्या?
15 मिनट 33 सेकेंड्स।
हैं?
15 मिनट 33 सेकेंड्स। मैंने नॉन
तभी
स्टॉप।
आ रहा है समझ में, तभी समझ में आ रहा है।
तो तूने क्या करा है? तूने इंटू 2 कर दिया क्या?
मेरा 34 में हो गया है, मैं 34 में पहुंचा।
तो
इंटू 2 नहीं किया है मैंने,
फिर कैसे पहुंच
मैं
गया?
पहले से 15 मिनट कर रखा था ना।
ओके
15 मिनट आगे हूँ तेरे से।
ओके, लगता है मुझे इंटू 2 करना पड़ेगा।
चल देखते हैं समझ में आता है कि नहीं आता। अजीब ही है।
आ रहा है समझ में। अरे ये क्या दबा दिया मैंने. हाँ आ रहा है.
Draw a picture like that. So can I put down these columns? I'll draw these columns as they are, and then I'll do a combination of them. So the first column is over 2 and down 1, right? So there's the first. And now I want. I'll sort of start it the same way, say maybe 2x minus y, and maybe I'll take no z's as a 0, and maybe a minus x and a 2y, and maybe a minus z is a, let me make that a minus 1. And just for variety, let me take minus 3z, minus 3y's. I should keep the y's in that line. and 4z's is, say, 4. Okay. That's 3 equations. I'm in 3 dimensions, x, y, z, and I don't have a solution yet. So I want to understand the equations and then solve them. Okay. So how do you understand them? The row picture is one way. The column picture is another very important way. Just let's remember the matrix form here, because that's easy.
Sup, guys?
The matrix form, what's our matrix A?
No more talking, only study.
Lord.
ये क्या ही है?
Our matrix
Hola,
A
Kat.
is this right-hand side, the 2 and the -1 and the 0 from the first row, the -1 and the 2 and the -1 from the second row, the 0, the -3, and the 4 from the third row. So it's a 3 by 3 matrix. 3 equations, 3 unknowns. And what's our right-hand side? Of course, it's the vector 0, -1, 4. Okay, so that's the way, well, that's the shorthand to write out the 3 equations. But it's the picture that I'm looking for today. Okay, so the row picture. All right, so I'm in 3 dimensions, x, y, and z. And I want to take those equations one at a time and ask and make a picture of all the points that satisfy. Let's take equation number 2. If I make a picture of all the points that satisfy all the x, y, z points that solve this equation, well, first of all, the origin is not one of them. X, y, z being 0, 0, 0 would not solve that equation. So what are some points that do solve the equation? Let's see, maybe if x is 1, y and z could be 0. That would work, right? So there's 1 point. I'm looking at this second equation here just to start with. Let's see, also I guess if z could be 1, x and y could be 0, so that would just go straight up that axis. And probably I want a third point here. Let me take x to be 0. Say x to be 0, z to be 0, then y would be -1/2, right? So there's a third point somewhere. Hold on, okay. Let's see. I want to put in all the points that satisfy that equation. Do you know what that bunch of points will be? It's a plane. If we have a linear equation, then fortunately, the graph of the thing, the plot of all the points that solve it, are a plane. So these 3 points determine a plane, but your lecture is not Rembrandt, and the art is going to be the weak point here. So I'm just going to draw a plane, right? There's a plane somewhere. That's my plane. That plane is all the points that solves this guy. Then what about this one? 2x minus 1. Your lecture is not Rembrandt, and the art is going to be the weak point here. So I'm just going to draw a plane, right? There's a plane somewhere. That's my plane. That plane is all the points that solves this guy. Then what about this one? 2x minus y plus 0z. So z actually can be anything. Again, it's going to be another plane. Each row in a 3x3 problem gives us a plane in 3 dimensions. So this one is going to be some other plane. Maybe I'll try to draw it like this. And those two planes meet in a line. So if I have two equations, just the first two equations in 3 dimensions, those give me a line, the line where those two planes meet. And now the third guy is a third plane, and it goes somewhere. Okay, those three things meet in a point. Now I don't know where that point is, frankly, but linear algebra will find it. The main point is that the 3 planes, because they're not parallel, they're not special, they do meet in one point, and that's the solution. But maybe you can see that this row picture is getting a little hard to see. The row picture was a cinch when we looked at two lines meeting. When we look at 3 planes meeting, it's not so clear, and in 4 dimensions, probably a little less clear. So, can I quit on the row picture? I'll quit on the row picture before I've successfully found the point where the 3 planes meet. All I really want to see is that the row picture consists of 3 planes, and if everything works right, 3 planes meet in one point, and that's the solution. Now, yep. You can tell I prefer the column picture. Okay, so let me take the column picture. That's x times, so there were 2 x's in the first. first equation minus 1x is, I'm just taking no x's in the third. It's just the first column of that. And how many y's are there? There's minus 1 in the first equation, 2 in the second, and maybe minus 3 in the third. Just the second column of my matrix. And z times no z's, minus 1 z's, and 4 z's. And it's those three columns, right, that I have to... combine to produce the right-hand side, which is 0, minus 1, 4. Okay. So what have we got on this left-hand side? A linear combination. It's a linear combination now of three vectors, and they happen to be, each one is a three-dimensional vector. So we want to know what combination of those three vectors produces that one. Shall I try to draw the column picture then? So since these vectors have three components, so it's some multiple. Let me draw in the first column as before. So like x is 2 and y is minus 1. Maybe there's the first column. Y, the second column has maybe a minus 1 and a 2 and the y's and minus 3, somewhere there possibly, column 2. And the third column has no 0, minus 1, 4. So how shall I draw that? So nothing in, this was the first component. The second component was a minus 1, maybe up here. That's column 3, that's the column 0, minus 1, and 4, this guy. So again, what's my problem? What this equation is asking me to do is to combine these three vectors with the right combination to produce this one. Well, you can see what the right combination is, because in this special problem, especially chosen by the lecturer, that right-hand side that I'm trying to get is actually one of these columns. So I know how to get that one. So what's the solution? What combination will work? I just want one of these and none of these. So x should be 0, y should be 0, and z should be 1. That's the combination. None of that, one of those is obviously the right one. So this column 3 is actually the same as b in this particular problem. I made it work that way just so we would get an answer, 0, 0, 1. So somehow that's the point where those three planes met, and I couldn't see it before. Of course, I won't always be able to see it from the column picture either. It's the next lecture, actually, which is about elimination, which is the systematic way that everybody, every bit of software too, of production, large-scale software would solve the equation. So the lecture that's coming up, if I was to add that to the syllabus, will be about how to find x, y, z in all cases. Can I just think again, though, about the big picture? By the big picture, I mean, let's keep this same matrix on the left, but imagine that we have a different right-hand side. Oh, let me take a different right-hand side. So I'll change that right-hand side to something that actually is also pretty special. Let me change it to, suppose if I add those first two columns, that would give me a 1 and a 1 and a minus 3. There's a very special right-hand side. I just cooked it up by adding this one to this one. Now, what's the solution with this new right-hand side? The solution with this new right-hand side is clear. Now I took one of these, and none of those. So actually it just changed around to this when I took this new right-hand side. Okay. So in the row picture, I have three different planes. Three new planes meeting now at this point. In the column picture, I have the same three columns, but now I'm combining them to produce this guy. And it turned out that column 1 plus column 2, which would be somewhere there is the right column. One of this and one of this would give me the new B. Okay, so that's like we squeezed in an extra example. But now think about all these, all right-hand sides. Can I solve these equations for every right-hand side? Can I ask that question? So that's the algebra question. Can I solve ax equal b for every b? Let me write that down. Can I solve AX equal B for every right-hand side B. I mean, is there a solution? And then if there is, elimination will give me a way to find it. I really wanted to ask, is there a solution for every right-hand side? So now, can I put that in different words? In this linear combination words? So in linear combination words, do the linear combinations of the columns fill three-dimensional space? Every B means all the B's in three-dimensional space. So do you see that I'm just asking the same question in different words? Solving AX, oh, that's very important. A times X, when I multiply a matrix by a vector, I get a combination of the columns. I'll write that down in a moment. So that, you see, but in my column picture, that's really what I'm doing. I'm taking linear combinations of these three columns, and I'm trying to find B. And actually, the answer for this matrix will be yes. For this matrix, for this matrix A, for these columns, the answer is yes. This matrix is, this matrix that I chose for an example, is a good matrix, a non-singular matrix, an invertible matrix. So those will be the matrices that be like this. There could be other, and we will see other matrices, where the answer becomes no. Oh, actually, you can see when it would become no. When could, what could go wrong? How could it go wrong that out of three columns and all their combinations, when would I not be able to produce some B off here? When could it go wrong? You see that the combinations, let me say when it goes wrong. If these three columns all lie in the same plane, then their combinations will lie in that same plane. So then we're in trouble. If the three columns of my matrix, if those three vectors happen to lie in the same plane, for example, if column 3 is just the sum of column 1 and column 2, I would be in trouble. That would be a matrix A where the answer would be no. Because the combinations, if column 3 is in the same plane as column 1 and 2, I don't get anything new from that. All the combinations are in the plane, and the only right-hand sides B that I could get would be the ones in that plane. So I could solve it for some right-hand sides when B is in the plane, but most right-hand sides would be out of the plane and unreachable. So that would be a singular case. The matrix would be not invertible. There would not be a solution for every B. The answer would become no for that. Okay. I don't know. Shall we take just a little shot at thinking about 9 dimensions? Imagine that we have vectors with 9 components. Well, it's going to be hard to visualize those. I don't pretend to do it. But somehow, pretend you do. Pretend we have, if this was 9 equations in 9 unknowns, then we would have 9 columns, and each one would be a vector in 9-dimensional space, and we would be looking at their linear combinations. So we would be having the linear combinations of 9 vectors in 9-dimensional space, and we would be trying to find the combination that hit the correct right-hand side B. And we might also ask the question, can we always do it? Can we get every right-hand side B? And certainly it will depend on those 9 columns. Sometimes the answer will be yes. If I picked a random matrix, it would be yes. If I use MATLAB and just use the random command, pick out a 9-by-9 matrix, I guarantee it would be good. It would be non-singular, it would be invertible, all beautiful. But if I choose those columns so that they're not independent, so that the 9th column is the same as the 8th column, then it contributes nothing new, and there would be right-hand side B that I couldn't get. Can you sort of think about 9 vectors in 9-dimensional space and take their combinations? That's really the central thought that you get kind of used to in linear algebra, even though you can't really visualize it, you sort of think you can after a while. Those 9 columns and all their combinations may very well fill out the whole 9-dimensional space. But if the 9th column happened to be the same as the 8th column and gave nothing new, then probably what it would fill out would be, I hesitate even to say this, it would be a sort of plane, an 8-dimensional plane inside 9-dimensional space. And it's those 8-dimensional planes inside 9-dimensional space that we have to work with eventually. For now, let's stay with the nice case where the matrices work. We can get every right-hand side B, and here we see how to do it with columns. Okay, there was one step that which I realized I was saying in words that I now want to write in letters. Because I'm coming back to the matrix form of the equation, so let me write it here. The matrix form of my equation, of my system, is some matrix A times some vector x equals some right-hand side B. Okay. So this is a multiplication, A times x, matrix times vector. And I just want to say, how do you multiply a matrix by a vector? Okay, so I'm just going to create a matrix. Let me take 2, 5, 1, 3. And let me take a vector, x to be, say, 1 and 2. How do I multiply a matrix by a vector? And just think a little bit about matrix notation and how to do that multiplication. So let me say how I multiply a matrix by a vector. Actually, there are two ways to do it. Let me tell you my favorite way. It's columns again. It's a column at a time. For me, this matrix multiplication says I take one of that column and two of that column and add. So this is, the way I would think of it, is one of the first column and two of the second column, and let's just see what we get. So in the first component, I'm getting a 2 and a 10. I'm getting a 12 there. In the second component, I'm getting a 1 and a 6. I'm getting a 7. So that matrix times that vector is 12, 7. Now, you could do that another way. You could do it a row at a time. You could do, and you would get this 12, and actually I pretty much did it here, this way. I could take that row times my vector. This is all the time. This is the idea of a dot product. This vector times this vector. 2 times 1 plus 5 times 2 is the 12. This vector times this vector. 1 times 1 plus 3 times 2 is the 7. So I can do it by rows, and in each row times my x is what I'll later call a dot product. But I also like to see it by columns. I see this as a linear combination of the columns. So here's my point. A times x is a combination of the columns of A. That's how I hope you'll think of A times x when we need it. Right now with small ones we can always do it in different ways, but later think of it that way. Okay, so that's the picture for a 2x2 system. And if the right-hand side B happened to be 12, 7, then of course the correct solution would be 1, 2. Okay, so let me come back next time to a systematic way using elimination to find the solution, if there is one, to a system of any size, and find out, because if elimination fails, find out when there isn't a solution. Okay, thanks.
वही कहा तो तूने बिल्कुल सही था वैसे। है मांचू,
हाँ बोल।
कहा तो तूने बिल्कुल सही बात थी वैसे।
20 मिनट के बाद नहीं समझ में आया ना?
नहीं समझ तो मुझे पूरा आ गया। मैं बोलने लगा था कि क्या बोलते हैं, इस बंदे ने जो 1 घंटे में मुझे जो चीज़ समझाई है ना अभी, वो ना मेरे कॉलेज में कभी समझाई है किसी ने, ना फ्री कोड कैम्प में समझाई है भाई। जो
अबे नहीं पता है, इसके लेक्चर्स बढ़िया होते हैं।
पीछे का कॉन्सेप्ट है ना जो 3D वाले स्पेस पे, वो बंदे ने करा दिया भाई 1 घंटे में।
अब समझा मैं क्यों तेरे को यार मैं बोलता रहता हूँ, क्यों मैं तेरा दोस्त हूँ असली।
हाय हाय समझ गया भाई।
अब यार पे ब्रेक लेना चाहिए यार। अब
3 घंटे हो गए मैं पढ़ते हुए।
हाँ, अपने पापा से बोलना है।
तू थक गया क्या?
थका नहीं हूँ, पर पता है खाने का मन कर रहा है।
मेरे को भी।
खाते हैं दोनों एक साथ ही, एक एक ऐसे दिखा के खाएंगे।
स्ट्रीम चल रही है।
अरे मैं नहीं हूँ ना।
तू है ना, तेरी वीडियो दिख रही है।
नहीं दिख रही, तूने हटा दिया था, अच्छा किया था। मैं
अच्छा
तो गया था ना पानी भरने।
बीच में हटा दिया था मैंने सोचा कि
हाँ सही किया बे, पता क्यों? क्योंकि मैं उसमें पानी भरने जाना था।
हेलो,
अभी भी हटा ही रखा होगा। अच्छा है, हटा
मैं
रखा होगा।
ब्रेक ले रहा हूँ आधे घंटे की।
नहीं हाँ, आधे घंटे की ब्रेक ले, शाबाश। हाँ पापा, हाँ भर दिया पापा पानी। हाँ क्या बोल रहा था?
तेरे घर वाले उठे होते हैं इस टाइम?
क्या बोल रहा है चिंटू?
मैं कह रहा हूँ तेरे घर वाले उठे होते हैं इस टाइम?
उठे होंगे किसी काम के लिए।
कौन सा काम?
बाद में जवाब दूंगा।
ये स्ट्रीम पे हमारे क्या चल रहा है नाप शनाप। चलो जी, एक लेक्चर हो गया।